Welcome on online wireless mobile communication lecture series. Today our topic is the outdoor propagation model, in which we are having the some contents. That is, the first one is the introduction. First is introduction. Second one is the Longley Rice Model. After we followed the Korma Model, and the last we have took a last topic, Hatha Model. We have seen previously radio transmission in a mobile communication system often takes over in a irregular drain. Irregular drain. In such scenario, irregular drain, the profile of a particular area needed to be taken into the account. So, for the estimating the path loss. Previously we have taken the only the line of sight, direct line of sight, side, and between the transmitter and receiver we calculate the direct path loss. In this scenario we are not including the deviation obstacle amount of radiated signals. So we are now calculate to drain profile may vary from a simple curve earth profile to a highly mountainous profile. The presence of there is a tree, lot of trees, and there are lot of buildings and other obstacle. This trees, this building, these mountains should be kept into the consideration, and a number of propagation model to be given on this base are available to predict the path loss or over a irregular this irregular drain. So what happened in this irregular drain? A number of propagation models are available to predict the path loss. While all these models aim to predict the signal strength, and of this signal strength means it the received signal strength. This received signal strength means actually we have discussed on the path loss scenario. What is the received signal strength in the several urban scenarios. There is a quasi area, there is a open area, and there is a sub-urban area, there is a dense urban area. A lot of areas which are effective. The factor of this propagation channel model, path loss model, and the idea is behind that we accurately, or we are more or less we are having the accurate prediction of this signal strength that is certain in instant. There is a one model which is came out that is called the Korma Model. Korma Model. Before this model, there is a one first model is called Longley Rice Model. A Korma Model is given in 1968, and this Longley Rice Model is a particular the specific particular point area that is called the sector. The method is very widely in their approach because of the complexity and the accuracy. The most of these models are based on the systematic interpretation of measurement data. So we this measured data obtained from this different service area, and some of the commonly used outdoor propagation models are now commonly used. There are basically three more than this model, but popular models are Longley Rice models, and Korma models, and Hatha models. So take this Longley Rice model. In Longley Rice model is applicable to point-to-point connections, and where the transmitters or receiver are communicate to in the range of frequency which is 40 megahertz to 100 gigahertz. Over the different kind of there is a different kind of terrain, and the median transmission loss is predicted using the path geometry of drain profile and the refractivity of the this I know there is a three layers. The toppermost I know this troposphere geometry optics techniques are primarily there is a two-ray ground reflection model are used to predict signal strength within the radio horizon, and in diffraction losses over the isolated obstacles are estimated using the Fresnel Kirchhoff knife edge model. Forward scatter theory is used to make the iso scatter prediction over long distance, and the far field diffraction losses in the double horizon path are predicted using the modified Ball-Bremer method. So the Longley Rice propagation prediction model is also referred to as the ITS irregular terrain model. So it having the one more name that is called ITS irregular terrain model. So Longley Rice model is also available as a computer program. It is also available on a computer program to calculate the large scale median transmission path loss is relative to the free space loss over a regular terrain for a frequency between 20 megahertz to to the 20 megahertz to around 10 gigahertz. So the given transmission path, the program, this computer programs took as it is input transmission frequency. This is the transmission frequency, and path length, polarization, antenna heights, surface refractivity, effective radius of earth, and the ground conductivity, ground dielectric constant, and other like a phenomenon that climate. So this program also operate on the path specific parameter such as horizon distance of antennas, horizon evolution angle, angular trans horizon distance, drain irregularity, and other specific inputs. The long rise methods operate in two modes. When it details drain path profile is available, the path specific parameter can be easily determined, and the prediction is called point to point prediction. And on the other hand, if the drain path profile is not available, it is depend on the drain profile. If it is available, then point to point prediction is determined, and when the path is not available, the long rise method provide the techniques to estimate the path specific parameter, such as the prediction is called area mode prediction, and this is available when the terrain profile are not available. So there has been many modifications and correction in the Longley Rice model, and since its original publication. The one important modification deal with the radio propagation in the urban areas, and this is particularly relevant to mobile ratio. This modification introduces an active term as an allowance for the additional attenuation due to urban clutters, near the receiving antenna. This extra term is called the urban factor, and this urban factor has been derived by comparing the prediction by the original Longley Rice model with those obtained by Korma model. So one shortcoming of the Longley Rice model is that it does not provide the way to determine the correction due to environment factor, and in the immediate vicinity of the mobile receiver, and consider correction factor to account for the effect of building and the others reflected structures. Further, it is a multipath is not considered. So we can say a Korma model who measured the transmission and reception power, and then plotted a graph on which we now find out the path loss. So it is the graphical representation where all the data are taken by the instruments and put it to make this graph. So it is a empirical formula, empirical approach. In this empirical approach, there are so many factors which are now we can calculate the received signal strength in the several urban scenario, and there have been the several propose lot of set of data to effect this our consideration, give a accuracy and convenience to predict the signal strength at the receiver end. So it is a Korma model is one such a model which provides a accuracy in terms of the to find out the path loss in multiple obstruction in drain, irregular drain phenomena. So if we talk about the outdoor propagation propagation model, there is a okumura model is widely used, or convenience model to cover this our path loss model, because the outdoor radio transmission took place over a irregular drain, and the irregular profile must be taken into the consideration for the estimation of the path loss. And there are the trees, buildings, hills, desert, water bodies. These are is also taken into the consideration. The outdoor propagation models gives the so many models, but these three models are is important, and which are already we have seen the Longley Rice Model. Now move towards the Korma model. In the early days, the model were based on the empirical studies. This Korma models are basically applicable to predict the signal, received signal, signal strength in the urban area. So the presence of this trees, building, other obstacles are also be taken into this Korma model. So it is the one of the most widely used model for signal prediction in urban areas. This model is applicable for the frequency in the range of this range is rises from the 150 megahertz to around 1920 megahertz. So a Korma model, first of model okumura model, having the frequency range 150 megahertz to the 1920 megahertz. Although it is a typically extrapolated up to the 3000 megahertz, and the distance of 1 kilometer, distance of 1 kilometer to 100 kilometer is taken into the consideration. It can be used for the base station antenna height, which is ranging from the antenna height of the base station, that is ranging from 30 meter to the 100 meter of base station of the base station. And a Korma developed a set of curves giving the medium attenuation relative to free space, which is given by AMU in urban areas or over a quasi area. It is in urban area, it is also in quasi smooth drain area, and the height of the base antenna is around 30 meter to 1000 meter. Okay, and the base station effective height, which is given by h of TE, is of 200 meter, and mobile antenna height, which is given by h of RE, is 3 meter. This is the base station effective antenna height, and this one is the mobile antenna height. So these curves were developed from extensive measurements using vertical omnidirectional antenna at both the base and the mobile, and are plotted as a function of frequency in the range of 100 megahertz to 1920 megahertz, and a function of distance from the base station in the range of 1 kilometer to the 100 kilometer. To determine the path loss using the Korma model, the free space path loss between the point of interest is first determined, and then the value of AMU. This is the value of AMU, attenuation factor, attenuation factor, is read from the